And welcome to 13.2, the nature of liquids. Hey, recall in 13.1 we're dealing with the nature of gases, and we introduced you to the idea of the kinetic molecular theory, describing how particles behave. And that really does extend all the way through the nature of liquids as well as solids. So we're going to be revisiting that concept here as we go. Now here's the deal with liquids, and let me go ahead and get my pen ready. We'll go ahead and stay with green color. In gases, there are no attraction or attractive forces, no attractions between the particles. However, in a liquid, the particles are attracted to each other, which keeps the particles close together. So here's the deal. If you have a container with gas particles, and we'll just make them as little dots, okay, as opposed to a container with a liquid in it, we'll just make wavy lines just so that we know that it is in fact a liquid. These particles are going to be tightly packed together. Now they will not be in a regular pattern because they're moving around one another. They have enough energy to overcome attractive forces to where they can move around each other, but the attractive forces are strong enough to keep them tightly packed together, which is why they group together in a liquid, and they also flow together. If I change this, let's go with a red color for this one. These particles here, if this is moving in this direction, and this is moving in this direction, and this is going in that direction, or whatever, the forces of attractions are so small that they do not interact with each other. And so these particles can literally go anywhere in the container, which means they're blowing around in the middle of the atmosphere, or in the middle of the room, or the middle of the container. As opposed to these particles over here with the liquid, say if we trace this particular particle, it's going to get bounced around, move around here, it's going to flow around here, 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 here. It's going to be very random in its motion. So it's allowed to move around one another, but the attractive forces keep them very, very tightly packed together, which makes them flow together. All right. Moving on with our paragraph still. Scrolling down. It is these forces of attractions in the disruptive motion of the particles that determine the physical properties. Let's scroll down here. Physical properties of the liquids. Depending on how tightly these are held together, that will determine how quickly they flow together. For example, syrups and molasses are really, really attracted to one another, so they tend to stick together, so they flow very, very slowly. Other particles are very loosely attracted to each other, so the liquid flows very, very quickly. All right, that deals with what's called viscosity. Another way we can talk about these attractions, and a lot of people don't just call them attractions, some people call them intermolecular forces, and they'll abbreviate them IMFs. These IMFs, or attractive forces, also determine when they're going to freeze, when they're going to melt, when they're going to boil, when will they condense. All those types of properties that deal with liquids are determined basically by how these things are attracted to one another. If you take a look at this particular picture, or set of pictures down below, you have bromine. This is bromine, B-R-O-M-I-N-E, bromine. It has a symbol of Br. This is liquid bromine. You can see it's sticking together even as you pour it out of a beaker, or out of a flask into a beaker. Similarly, this is gaseous bromine. So here's your liquid. We'll put that as an L, a cursive L in parentheses, and we'll put this as a G in parentheses. Here's your gas. That also can be poured out just like a liquid, but yet the particles are not stuck together. So that's the whole idea here, is how much these particles like to stick together. and that's what's going to be determining the properties of these guys. In the next podcast, we're going to take a look, and scrolling down here. Whoop, no, we're not going on to the next podcast. We want to talk about evaporation and vaporization. All right, so stay tuned here. Vaporization. Vaporization is simply going from a liquid to a gas. Now that can be achieved a lot of different ways. Typically it's achieved by raising the temperature, and it can be done by boiling. But you can also actually change the pressure and get it to vaporize as well. So we'll just leave it at that. Evaporation is also going from a liquid to a gas, but it's done at the surface of a liquid that is not boiling. Obviously, water evaporates off of lakes and streams and whatnot in the middle of the summer. Actually, they evaporate all the time. But obviously Lake Erie or Lake Michigan or the River Raisin or whatever lake or stream that you're by is not necessarily going to be boiling. Not necessarily. It will not be boiling. But the water does leave the liquid phase and go to the gaseous phase. So let's talk a little bit about what's going on there. Again, let's draw our containers. Okay, here's our liquid. And here's our particles stuck together, loosely stuck together, able to move around one another. And that should be good. If we take a look at what's going on at the molecular level, when something boils, what it means is that this thing has enough energy to overcome the intermolecular forces or the attractive forces and go into the vapor phase. Think of them as magnets. Magnets will be stuck together, but yet if you pull on them enough, or if you give the magnet enough energy, you can dislodge it from the other magnets, and it can be separate from them. That's basically what these particles are doing. As these things boil, eventually all of the particles will have enough energy to go into the vapor phase, and then it'll be done boiling, and they'll all be gases. On the other hand, evaporation will look something like this, where if you have your liquid, and again here are your regular particles closely held together by the attractive forces. Alright. What happens there is there's only a certain number of particles that have enough energy to overcome the attractive forces. Recall this diagram here that we went over in 13.1, where at any given temperature there's a distribution of speed or distribution of kinetic energy, where you're going to have some particles that have a high amount of energy. Remember, if this is Ke, kinetic energy, this is high kinetic energy right here, this is moderate kinetic energy and low kinetic energy. There's a certain portion of particles that will in fact have enough energy to overcome the attractive forces. Not all of them, but a few of them will. So those water molecules, or whatever the liquid is, will go into the vapor phase. That is evaporation, as opposed to just regular vaporization, which tends to be boiling. All right. Now, in the next podcast, I'm pretty sure we're going to be moving on here. There we go. In the next podcast, we're going to take a look at vaporization in open and closed containers, talk about vapor pressure, and then boiling points. We'll see you next time. Stay tuned.